Swayam Prabha. Digital India. Educated India.
The key points we have learned yesterday. One of the key point was the input source and output load. Okay. Need to be isolated from the core amplifier circuit so that DC biasing remain intact. So that's the one of the okay, so you remember that so we need to have a coupling capacitor here, okay, and whatever be our biasing mode, okay, in case of whether it is single resistor biasing or voltage divider biasing, okay, we need to isolate this input signal from this core biasing circuit, and also we need to isolate the output load, okay. So this C1 and C2 is a coupling capacitor, okay, and these two coupling capacitor is very important so that we can keep our IBQ, ICQ and VCQ intact, okay. So that is one key message or one key concept we saw yesterday, okay. Then we discuss the effect of biasing. One of the in this digital pad, somehow my writing is extremely poor, okay. So biasing effect on C amplifier performance, in that we have seen one case which is basically single resistor biasing, okay, and if we so there is input AC signal which we want to amplify, okay, and you remember if we draw this input signal, redraw the circuit to find the input signal gain, input impedance and output impedance. It is pretty straightforward, because for that you need to AC ground this capital VCC, because this is the DC voltage. So this RB will effectively come here, okay, and then you can easily find out the gain, right? So that is what we did yesterday. So we so RB effectively becomes between base and ground, okay. So you see RB is not attenuating the input signal, so it doesn't have effect on the gain of the circuit, okay. So gain will remain the same, that is we have discussed in the last class. If there is R naught, you need to write R naught in parallel, and if there is no R naught, you can directly write input AC signal. Okay, the input, I mean minus GMRC. However, this RB has effect on the input impedance, which is again obvious because RB will be in parallel with R pi. Okay, so the new input AC input impedance will be R pi parallel RB, and also the R out will remain the same. Okay, so this part we have done yesterday, and also then we have started our discussion about the second biasing circuit, which is much more popular, voltage divider biasing. Okay, in that case also it is you can intuitively guess that your gain will remain unaffected for this R1 R2 resistance, simply because these two will come in parallel when you draw that corresponding AC circuit. Okay, so this is your RC. Okay, we are taking V out here. This emitter is grounded in this particular case, and you see R1 and R2 is basically parallel, and they are between base and collector, because this VCC is grounded for our AC analysis, right? And we can again straight away write the gain. Gain will be same as before. Okay, but your input resistance or input impedance going to change because of this R1 R2 in parallel, and that is parallel to R pi, right? Again your output resistance will remain the same, right? So this part again we have discussed in the last class. Now one small modification we want to do is, like, if we have emitter degeneration, that is also will not be very difficult, but let's discuss that to complete this biasing portion. Okay, so we have now additional resistor RE, which is the degenerate emitter degeneration resistor. Okay, so this is our circuit then. Okay, in that case, if we draw the corresponding AC AC circuit, it will be similar to what we have drawn before. The only difference is there will be extra RE here. Okay, so this is your right. In that case, again you can find the input resistance. Let's write the gain first. Gain is, again, it will not change the gain simply because R1 R2 is not attenuating the input signal, you see. So your gain here, I mean voltage here and voltage here is the same, so your core gain equation will remain the same. However, you remember the gain here is we have written yesterday in this configuration is like this, because of this additional emitter degeneration resistance. The gain formula is this for this particular circuit. However, your input impedance will deteriorate because R1 R2 in parallel, and R1 R2 in parallel, and that is again parallel to your effective you remember that beta plus 1 RE. Okay, so initially this was our input input resistance along with this R1 R2 in parallel. Okay, so this additional term will come into picture because R1 R2 is here, right? So this is your input impedance, and corresponding output impedance again we know, right, that we have calculated yesterday, you remember, right? So again we can improve the gain by bypassing this RE and all that with a capacitor that we have discussed already. So this is in a nutshell as far as the biasing is concerned, how biasing changes the performance of the C amplifier. If we generalize everything, okay, let's have one more configuration, not configuration, but if we generalize everything, then we have to add like one load resistance, one source resistance of the input signal, and see how then the situation will change. Obviously, if you add a source resistance, that will deteriorate your uh, your gain. Okay, uh, so this is more generalized case where we have a load resistance, okay, which is isolated by a resistor C2 from the biasing circuit, and we have a source resistance which is associated with your V in, okay, and of course isolated this source with a capacitor C1 from this biasing circuit. So this is like more generalized situation, and if this is the case, of course you can again redraw this circuit. You remember we have this we have this uh, um, voltage divider calculation. So you can think this as a voltage divider, this R1 R2, of course. Of course, then you might argue like some portion of current is going this way, and some portion is coming this way. This whole current is divided in two parts. I'm talking about DC current, okay? So but if this current IB is much smaller than this whole current, then you can basically approximate it as a voltage divider. Anyway, so if we can by that way we calculated it before the so R1 parallel R2, okay, and there is RS here, there is V in here, okay, and this is RC parallel RL. Let's put that way, because RC and RL will be parallel, because you see RC is grounded. So if RC is grounded and RL also grounded, and both this point, this collector point here and the point here is basically effectively the same point, because the capacitor is chosen in such a fashion that capacitor is short for the AC signal. So effectively RC and RL is parallel. Okay, so here at the input side R1 R2 is parallel, and here RC and RL is parallel, and RS is here. So you can see that as RS is here in series with this source, so effectively entire V in is not coming to the base of the transistor. Okay, so that way the gain will deteriorate because of the presence of RS. Okay, that is, you can intuitively guess. In fact, this will effectively form a voltage divider. Okay, and we need to find how much voltage is coming here, because then you know the gain, right? How much voltage is coming here, then you know the gain. but effective gain will be V out over V in, right? So if this is our point X, we have done this calculation before, so we can write Vx over V in, okay, if this is the point X. So what is the resistance here? Resistance here is R1 R2 parallel, remember R1 R2 parallel, and in along with that it is parallel to R pi plus beta plus 1 Re, right? So this is the effective resistance here, okay, and another resistance is Rs. So that divided by R1 R2 R pi plus beta plus 1 Re, okay, plus Rs, right? Because this is the entire this denominator, you see the entire resistance, okay, out of which we need to find how much is in the voltage at Vx. So we are multiplying it with this, right? I hope this part is clear to you. This is because we have developed this concept stepwise, so I can directly write that. So this is the this part. So if I, so this part here, okay, basically effectively this part, right? This R1 R2 R1 parallel R2 parallel R pi plus, because this is the input resistance, you remember, and so that if you connect with if you can add with Rs, that's the entire resistance. So it is acting as a voltage divider circuit. Now so similarly you can write V out over V in, okay, that can be written as Vx over V in, V out over Vx, right? Now Vx over V in is this, Vx over V in is this quantity, and V out over Vx is already known to you, right? Already known to us. What is that V out over Vx? V out over Vx is RC parallel RL, right? Whatever resistance present at the so this is this particular term is I am writing here, okay, RC parallel RS. So you remember the resistance connected at the collector, okay, divided by 1 by Gm plus Re, you remember, okay. So that is again straightforward from the concept we developed yesterday and day before and earlier classes. So this is the numerator is the resistance connected to the collector divided by the resistance connected to the emitter, that is Re, plus the input resistance you see from there, that is 1 by Gm, right, when there is no Re. So this is the equation if you consider this V out by Vx, right? That is pretty straightforward. So and of course there will be a negative sign, right? Now what about this first term? And first term is written here. Let me write it once more. So the first term will be will be this, okay. Let's I am not writing it, please write it in your note. So first term will be this I have written on top, okay. So these two, if you then so this is basically the gain of your circuit, okay. And of course you see gain will change a bit because of this Rs, presence of Rs, okay. Now if you see Niemann's book, they have, instead of this voltage divider, they have found out the V Thevenin and R Thevenin. Effectively both are same, but you can find out your V Thevenin and R Thevenin of, so you can find out, let me do that then, okay. So you can effectively find out V Thevenin of R and R Thevenin of this portion, okay. I am going to a new slide. Let's I have let me draw it once more. So whatever we have done, you can recalculate and came to sort of similar expression. Okay, so this is your RC parallel RL, this is your V out, and this is your R1 R2. So what I am trying to do, I am trying to you remember we calculated we have some calculation in the same direction using V Thevenin and R Thevenin of this kind of circuit. Although we are not discussing the common emitter amplifier portion, we are discussing the biasing, but we have used V-Thevenin and R-Thevenin configuration to find out the corresponding expression. So you can basically change this portion in the form of V-Thevenin and R-Thevenin. Okay, so your corresponding V-Thevenin okay, obviously will be R1 parallel R2. Those who know the Thevenin theorem, I think they can easily appreciate this. So this will be your V Thevenin. What about R Thevenin? R Thevenin again you can write RS parallel R1 parallel R2, right? You remember? So if we do that, we can straight away redraw this circuit in the form like this is your V Thevenin. Okay, and this is your you can change everything to R Thevenin. Okay, and then have your RE and corresponding blah 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 RE RC parallel RL and all that. So we can again straight away write the gain okay by RC parallel RL over 1 by GM plus RE. And you remember, I think in the yesterday's class we have found out this, right? You remember we have this RB, and one of you asked we have divide the whole thing with beta or beta plus 1, and we have this expression, right? So this is this additional term you will get because of the presence of R Thevenin. In our discussion before, it was RB. You saw yesterday note. I think it will be clearer. But along with this, of course, there will be an additional term which is R1 parallel R2 plus divided by R1 parallel R2 plus RS. Okay, this is because of that voltage divider. So this I mean you can try back home these two, this equation here and equation in the previous slide, they are effectively the same thing. Okay, if you simplify it, you will see that they are effectively identical. Okay, so we have this because of this R Thevenin, there is R Thevenin, you need to divide with beta plus 1. Okay, and there is R1 parallel R2 R1 and in the numerator this additional term, and in the denominator R1 parallel R2 plus RS. Okay, so this is I am stopping the common emitter configuration amplifier discussion here. Now what we will do, we will discuss briefly other two configurations. You remember we said that we will discuss three configurations as far as the amplifier is concerned, amplifier circuit is concerned. So we have so far we have concentrated only on discussing common emitter mode. So let's start another topology, which is common base. Okay, and we will see that whatever concept we have developed in common emitter topology will be equally valid for common base, and we can straight away write things very easily, and we can basically very briefly discuss. So in the our main motto is to have the concept with common emitter, but we will discuss common base and common collector very briefly, try to understand its application and how it is different as far as gain is concerned, as far as the input output resistance is concerned, and so on, so that in future you know which particular topology you need to use depending on the application. Okay. Now in common base topology, as you understand from our discussion of common emitter, the base will be common between input and output, base in common between input and output. So we can straight away draw a common base circuit as an amplifier. So in case of common base, your base will be common and it will be grounded, right? So your base is common and it is basically AC ground, whereas your you apply your input signal at the emitter, and you have your output signal at the collector. Okay, this is your VCC. So this is a common base configuration where the base is AC grounded and base is in between your input and your output. Okay. The corresponding small signal model, again we can straight away draw. We will have R pi, we will have GM V pi. Okay, here V in we are applying at the emitter, and of course R pi is basically grounded because that is AC ground, and this is also there is RC, and that is also AC grounded one part, and this is your V out. This is again pretty straightforward from our common emitter discussion. Okay, the only difference here is instead of V in applying at your base, you are applying V in at the emitter. Okay, and base is basically your AC ground. In the base you have applied a DC biasing voltage. Okay, and another voltage is VCC, right? So this is the common emitter common base topology. So you can straight away find the gain of the circuit in the same fashion we did in our common emitter topology discussion. So you see here V pi is, again this is your V pi as usual. Okay, so you see V pi and V in is polarity is opposite. Okay, so V pi is minus V in. So if that is the case, you can straight away write gain, which is V out over V in equal to GM RC. The only difference here is so you see the gain is same as far as the common base or common emitter topology is concerned. The only difference is here the signals are in phase. Okay, so the gain is basically positive. Gain is positive, whereas in common emitter mode we saw that the signals are out of phase 180 degree, and gain is there is a negative sign in case of common emitter configuration. Now in the same way we can also discuss that VCC has an important role to play as far as the gain is concerned. You remember we had this discussion in the common emitter configuration. So so we can so I am redrawing it. You don't have to redraw because it is a new slide. I'm just redrawing it. So you see this AC, this DC voltage has an important role to play in the gain that we have discussed before, and this headroom is important. So you can this is your AV is equal to GM RC, and you remember GM is IC over VT, right? IC or ICQ over VT, that is basically your GM, and of course then you can write this, okay, because I am assuming again, like last class, I am assuming, so this is your VBE, and I am thinking like the voltage here should be at least equal to, although one of you asked me in the last class yesterday that what we should consider this VCE, should be 0.2 volt, but that if you take it is 0.2 volt, it is really in the saturation, okay. What we try to discuss, we always consider this Vy, okay, greater than equal to Vx, to have like safely it is in the forward active mode. So that was just the argument I think I wanted to put forward yesterday, but it's up to you. You can consider that as 0.2 volt, but if you consider that at 0.2 volt, then it is really in the deep in saturation. But if you consider Vy is close to or more than Vb, then it is, you are safely in the for the forward active mode, okay. So if you have like if you consider Vy is equal to Vbe, then you can write this as Vy equal to Vb. So this is your sorry, so this is your IC, okay. So of course there is an additional Vt term, so this RC will cancel out. So this you see this VCC has an important role to play as far as the gain is concerned. The same kind of discussion we had it for this common emitter stage, okay. Now let's move on and look at what about the input resistance or input impedance of such an amplifier, okay. Again, if you use the concept we have discussed already, we can straight away write that this will be this is your Rin, okay, and if this is your Rin, then your Rin will be, you remember Rin will be 1 by Gm, isn't it, that we have discussed long ago. So Rin will be, if you see from here, and if your base is AC ground, then it is 1 by Gm, right. So your Rin here is 1 by Gm. So if Rin is 1 by Gm, we can safely say that the input resistance of such an amplifier is very low, because you see Gm equal to IC Q over Vt, right, and say IC is IC is of the order of milliamps. It is usually of the order of milliamps in conventional BJT. If it is like 1 milliamp ICQ, say if ICQ is 1 milliamp, okay, then what will happen to this Rin? You see Rin will be 26 ohm, right. Rin will be 26 ohm, because that will be then 1 by Gm is Vt over ICQ, and Vt is close to 26 millivolt over 1 milliamp, so that's basically 26 ohm. So you see this is much lower than Rin we get in case of common emitter stage, because in case of common emitter stage your Rin for CE, your Rin is R pi, okay, that is beta over Gm, right. So that is much larger than what Rin we get in case of common base, okay. So so that represents, although the gain remain the same with common emitter stage, the input impedance is much lower. In fact, if you see Rajabi's book, there is elaborated discussion where we can use this common base configuration. Usually we use common base configuration in case of for example transmission line in microwave. In transmission line, the characteristic impedance is around 50 ohm, Okay, so we can tune this circuit and in such a way so that we can match this input impedance with the transmission line line characteristic impedance, so that probably then we will have very less reflection in transmission line and all that. Okay, so one of the application of such a circuit where in transmission line where the input where the circuit resistance is very low, and we have to match the circuit resistance so that the reflection from such a circuit becomes lower. Okay, now what about the output output impedance? Okay, output impedance, you can again just draw the circuit once more. Say I have R naught here. Okay, that is the because of RD voltage, and we have RC, you see. So this is you can connect again, you can connect here your test voltage source, and you get the current from Vx Rx. You can find out the R out, right? But here I'm just not doing that. It is very straightforward. It is R out will be RC parallel R naught. You see from the drawing, RC is here and it is parallel to R naught, because R naught is again one side of R naught is grounded, so they are effectively parallel. Okay, so we can straight away write it is RC parallel R naught as far as the output resistance or output impedance is concerned. So output impedance is same as far as the C stage and CV stage. Gain is also magnitude wise same. The only difference is here the input impedance is lower. Okay, let's discuss it little bit more. Then we will stop the discussion on common base stage, and I will encourage you, those who are interested, to go through much more and read about the biasing effect of common base stage and all that. Okay, so let's now consider if we have resistance associated with the input AC signal, then how this voltage gain will change and all that. Okay, so if we consider that Vin has a if we consider source resistance, okay, and try to find out the gain. Again, I think these are pretty straightforward and you should be able to do it by yourself, because we have or in Rajavi's book they have developed things very slowly, stepwise, so that things are more clearer. So you see, this is our circuit. Okay, and we have this Vin and we have this RS. Okay, so this is the circuit where I have additionally introduced this RS, which is associated with this Vin. Okay, and try to find out the gain. Now in this case, if this is my point X, we always divide things so that whatever we have developed already we can relate with that. So if it is the point X, then gain from here is GMRC, that you know. Okay, but this additional RS is now there. But here if you see carefully, if you see from this side, there is 1 by GM, right? So effectively your GM is coming, 1 by GM is coming as a voltage, 1 by GM, and RS is acting as like a voltage divider where this is your point X. Okay, so if that is the case, then we can again straight away write what is Vx. Vx will be 1 by GM, so that resistance divided by RS 1 by GM multiplied by V, that is your Vx, right? And so you can restructure the equation. Okay, and you can find out the gain, because we know already that V out over Vx, because it is not V in, it is Vx. V out over Vx is GMRC, that is already known to us. And if Vx is this, so we can straight away find V out over V in. Okay. I'm going to the next slide. I hope you managed to write it down. So that is V out over V in, that is V out over Vx multiplied by Vx over V in, and V out over Vx is known to us already, that is GMRC, and Vx over V in, if I go to the previous page, Vx over V in is this value. Okay, 1 by 1 plus GMRS, right? So 1 by multiplied by 1 by 1 plus GMRS. So you see this is nothing but GMRC over 1 plus GMRS. Okay, so you can write, you divide, you divide both numerator and denominator with GM, and we have this is the gain formula. Now interestingly, you see that this gain looks like exactly this gain here looks like same the gain we got in the common emitter stage, you remember. So in case of common emitter stage, if we have like if we have a if we have RE and RC here, okay, the gain we found out is exactly same. The gain we had in C stage was RC over 1. Of course there was a negative sign, that negative sign will not be here. Okay, plus RE, you remember. So it is exactly same the gain we got in common emitter stage, provided there was a emitter degeneration. Okay, so interesting. I think you if you relate these things, it will be very easy for you to remember. Okay, the corresponding we can find out the corresponding R out also. Okay, we can find out the corresponding R out. For finding R out, or you have to ground it, whatever it is. So you need to, you can I mean in the AC signal part you can directly ground this. So this was our circuit, and what we want, like we want to find out R out, right? Because we have already the gain formula with us, which is same like common emitter degeneration circuit gain. Okay, the only thing is here S is there, which is the resistance associated with the source voltage. Okay, in resistance associated with your input signal. Now if we find out if we want to find out the R out, let me redraw the circuit once more. This is AC grounded, this is also AC grounded, so we can have like RC here. Okay, you can put your test voltage and Vx and Ix and find out what about Vx over Ix, right? And so this is your RS here. okay, and you remember we need to ground that input signal. What about so we can consider there is R naught if you are interested to include your voltage early voltage effect. Okay, so this is our um, small signal circuit if we want to find out R out. Okay, so if you if I say this is my R out 1, okay, this is my R out 1. So if you remember our yesterday's class discussion, R out 1 can be straight away written. This I have done already in the yesterday's class. Okay, uh, the only difference is there it was RE. You remember we were using RE and we had this formula, and you remember we had it we had whether so this was the formula, you remember, and we were finding out like whether RE is much greater than R pi and RE much less than R pi, two cases, and in one case we found out like beta times that of R naught we got, and in one case probably we got 1 plus GM RE times R naught. These two cases we got. I think you if we so in one case we had like RE much greater than R pi, and in another case we had like RE much less than R pi. Okay, these two, this was like common emitter stage calculation we did it yesterday's class, right? So this will be the same formula, because you see the circuit is exactly same. Circuit is exactly same. The only difference is there was RE here as a emitter degeneration resistance, but instead of RE it is RS, but the circuit is exactly same. Okay, so you see your R out will be, so I'm using the same formula from yesterday's class. You can see the proof of that or how we came to this equation if you saw the yesterday's note. Okay, so I mean I can redraw if you want it, if it is difficult to visualize, I can redraw that circuit and you will see it is exactly same. Okay, so in case of this is my common emitter stage, this is my common emitter stage. Okay, and we were leaking R out from here. This is common emitter. Okay, what C stage, what about what we are doing here is exactly same, you see. So we are, what we are doing exactly same. um, so this is CB stage, right? CB topology, and this is C topology, so they are exactly same. So I am directly writing that R out 1, the only difference is you have to, R out will be RC parallel R out 1. Okay, that is the only difference we will have. Okay, I mean here also if you take RC, it is the same RC parallel the same equation we will get. Now the uh, last thing we will discuss today is basically uh, the last thing we'll discuss today is what about if there is a resistance at the along with the base terminal. So if I have a if I have Okay, so uh, so if this is the case where we have an additional RB at the base, okay, uh, then how this uh, how this our gain will change. The reason I'm discussing this, you will see it is very closely related to your common emitter configuration discussion we already have, and you can straight away will be able to relate the interesting relation we get. Okay, so again we can uh, uh, because if we have these examples in our discussion, then it will be easier to solve problem and visualize circuits in a more detailed and intuitive manner later on when you have like when you attend other classes. Okay, because circuit analysis is very important, and if you can intuitively see through the circuits, not just by having like 2-page mathematical calculation, if you just straight away see can see the circuit, that will be excellent. Okay, so that's the whole purpose of going through all these in stepwise form, so that you can appreciate the development. Okay, so again we can draw the input signal, I mean draw the small signal circuit like this. Okay, here it is GM V pi as usual. So we have to do some calculations to figure out the gain of such a circuit. Okay, say this is point P. Okay, now we know GM V pi is equal to minus V out over RC, that is this GM V pi is going through this RC. We have done that before, so V pi will be minus V out over GM RC. This we will use in a minute, so I'm just writing it down here. And also you see this is your V pi here, so the current passing through it also passing through RB, right? So this V pi over R pi can be written in the form, if I use this equation. Okay, so that's basically the current which is passing through the R pi and also RB, right? And this is nothing but V out over beta RC, right? Because GM R pi is beta. So again VP, you can find out VP, that is the voltage here, and VP can be written as minus of V out over beta RC, okay, multiplied by RB plus R pi, right? Because voltage here is basically the voltage drop across R pi plus voltage drop across RB. So this is the whole resistance RB plus R pi, and this is the current, right? So this is the current. So this current multiplied by whole resistance is the voltage Vp. What I am aiming at, I am trying to find out V out over V in, because that's the gain, right? So this is my voltage Vp is this. Okay, I can then write this Vp can also be written as V in, there is a V in, and also voltage drop at RS. Okay, voltage drop across RS. Okay, that if we can relate, we will be able to find out V out over V in. Okay, so that will give us the gain. So so we can write V pi over R pi plus GM V pi, that is the two currents. Okay, you see V pi over R pi is the one current, and GM V pi is another current. These two current is basically going through this RS, right? So we can these two current we can relate with Vp minus V in over RS, right? So if you do that and restructure your you put V pi as minus V out over GMRC, okay, and restructure the this equation, then you will end up with, I'm just skipping steps, so we will ultimately get we will ultimately get this. Okay, so this is our gain formula. If you remember, we had a little bit of tricks so that it looks better and it looks more we will be able to relate to whatever our discussion in the CE stage. So let's divide it with beta plus 1. You remember we did it yesterday's class. So if you divide it with beta plus 1, you will have 1 by GM. Okay, R pi by beta is GM, 1 by GM. So plus your RS plus your RB over beta plus 1. Okay, you I think you can appreciate this. We have this similar equation we got in our yesterday's discussion also. So again this gain is positive, and it is a similar expression we achieved when we had like RB and RE. So instead of RE here we put RS. So we had that similar equation which we got in the CE stage. Okay, so with this you can also find out your Rin. Okay, I'm just writing it directly. You can put in this you can put a test voltage, okay, Vx and Ia, you get Ix, and you can find out the corresponding Rin. Okay, I'm not doing that. I'm just writing the ultimate expression. Again, I hope you will be able to do it. Okay, so that will come as 1 by GM RB over beta plus 1. Okay. So you see, in other words, if you look your base, so this is your base which has a resistance RB. It is grounded. Okay, and of course I haven't considered R naught. So you can write VA tends to infinity, and if I look on this side, that is your Rin, right? That is your Rin, because we are applying voltage input. This is your 1 by GM plus RB. So RB is basically reflected here. Okay, but divided by beta plus 1. You remember in case our common emitter discussion, RE, what we are applying at the degenerated emitter, RE is reflected with beta plus 1. Multiplication factor was beta plus 1. Here it is like the equation in comes such a way that we are dividing RB with beta plus 1. Okay, again just to relate with our previous discussion. So with this I am stopping here today. So we sort of try to cover or give you a brief idea of common base topology. In the next class, what we will do, we will discuss common collector topology briefly. Okay, and see how common collector is different from these two topologies. Those who are interested, I will encourage you to go through and see if we apply biasing, how this will change the gain and input resistance and all that, if at all it changes the gain or input resistance in the common base configuration. Okay, so let's take a break now for a few minutes, and we will come back and uh,